You got it? All right, I'll begin with a word of prayer. Dear Heavenly Father, we, again, Lord, thank you for the privilege we have just to come here and talk about you openly. Thank you for these students. Thank you for your creation. We thank you for math, that you've allowed us to understand it. Thank you for your creation, Lord. I just pray you be with us today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So I want to talk about coordinate change. So basically, if you like, U-Substitution for multivariate integrals. And so it's a little bit more nuanced than some of the other things we've done. I mean, well, I guess the chain rule, right? The chain rule had some structure to it that wasn't present in your previous work also. But here's the basic setup. We want to think about some kind of change of coordinates. And so maybe we have some region that looks like this in the UV plane. And I'm going to suppose that that maps over to some kind of, I don't know, whatever, which we'll call, and there's a change of, the transformation T takes us from here to here. So T of S, let's say, is equal to R. So I'm going to call this thing over here S. And I'm going to call that thing R. And so a typical point, of course, in the UV plane is U comma V. A typical point over here is going to be X and Y. And I want to try to relate these two things, and an integral over S and an integral over R. In particular, I want to figure out how it is our goal. Let me just put our goal up here. Our goal is to write the integral, double integral rather, over S, all right, of f of uv du dv in terms of a double integral in x and y. This is my goal. All right. I demonstrated how this could be done in the case of polar coordinates last class. I want to up the ante a bit here and try to do it for arbitrary coordinates. So what you can think about is just like a little rectangle. All right, and I'm going to make that little rectangle bigger down here. So here we go. So that same one. And so this will be at, let's say, UV, all right? Now what happens to a little rectangle under the transformation T? I need some notation here. So let's say T is equal to XY. What that, of course, really means is that T of UV is equal to X of UV, Y of UV. So like a parameterization, but I'm thinking of it actually as a separate space for the sake of discussion here. Now, so if I have a little rectangle like this, what happens if you map it under T? Well, it maps over here to some other little thing, and it turns out that what it's going to map to is some sort of little parallelogram. All right, so if this corner, let's say, is UV, then this corner over here, that point would be T of UV. Now, how is the area of this little rectangle related to this little parallelogram? Right? What's the deal there? So let's see here. This rectangle would be something like delta U times U hat would be this vector, right? Do you agree? And this vector, the vertical vector, would be something like what? It would be delta V times v hat. So a little change in v, a little change in u, and the u hat and the v hat direction. What's the area here? Change in u, change in v, right? Little displacement in both. What does this rectangle map to if delta u and delta v are, delta u and delta v are really small? How can we approximate t? What's the approximation for t? Do you remember how that goes? We talked about this a little bit. One of the main reasons I talk about the Jacobian mapping is just for this time. So I probably, fine, I probably should really add a little, like, sub-knot here or something so that you think of it as a fixed point. Let's do that. So this point, we're talking about a fixed but arbitrary point there. So what's the linearization of this t about that point? So I could write t of, say, u naught plus delta u, comma v naught plus delta v. That is, to a very good approximation, t of u naught v naught plus the Jacobian matrix, which was what? Well, for the moment, let's just say, well, let me be more explicit. It's specifically partial x, partial u, partial y, partial u, partial x, partial v, partial y, partial v. That matrix at the point u naught v naught, I have to evaluate at that point that we're thinking about, and then times this column vector, bless you, delta u, delta v. This is the linearization of the coordinate of the transformation, and that essentially becomes an equality if delta u and delta v are very small. So if I consider this to be a little rectangle, right? Just consider a little, almost infinitesimal rectangle. It is going to map under this linearization of the coordinate change to another very small parallelogram. Now, how do I know that when you feed this thing, how do I know that this formula, how do I know that this maps? A rectangle to a parallelogram. And what's the area of the parallelogram as compared to the area of the rectangle? That's what we'd like to know. Well, what I can do is very simple. I can just study how the edges of the original rectangle map. So what happens if we, what is this, by the way, explicitly? This is what? This is the column vector delta u 0. And in terms of linear algebra, this is 0 and delta v like that. That's. So in particular, if I find a marker that's working, let's see here about this one. So if you look at it, t of let's see, how can I say this? Oh, phooey. I guess to be more careful, I should map this point. I really should map this point and that point, right? And then because this vector here is what we want to find, right? And this vector there is how do I find these two vectors that I just drew? Let me call them 1 and 2. Now see, one should be t of what? T of, let's see, what's, sorry guys. This point here is u naught v naught. What's this point? Right? What's this point here? So I need to figure out what is t of those points, u naught plus delta v, delta u rather, and what's t of so of course both of them give you t of u naught v naught. That's just the constant. Then I have plus the Jacobian matrix, which I'm just going to rewrite as xu, yu, xv, yv, if you don't mind. And let's see here, what's basically the formula that I wrote for delta u, delta v. Well, in this first case, delta v is 0, right? So we really just have what? We have delta u and 0, right? On the second one, I have 0 and delta v. So what does this give us? When you multiply this, what you get is you get x sub u times delta u comma what? Sorry, I'm jumping the gun here. Y sub u delta u. And this one I get, when I multiply the matrices, I get x sub v times delta v and y sub v times delta v. Oops, not equality, but plus, right? Now to actually find these vectors 1 and 2, what do I have to look at? I have to look at the difference between the endpoint and the base point, right? So all that amounts to is what do I need to basically do is just subtract. So 1 is really just t of u naught plus delta u comma v naught minus t of u naught v naught. That gives me what? That gives me xu yu times delta u, and 2 you'll have to zoom in on this because the green doesn't work well. I'm sorry, Mr. Vu. So those are these vectors 1 and 2, right? And my point to you is that the area is what? It's the magnitude of xu, xu, yu, cross product xv, yv. Now, I guess to be careful, I should just make these, when I say cross product, I mean think of them as three-dimensional vectors, fine. If it's bothersome, I'll add a 0 there. Now we can take a cross product. Is that better? How does this, what does this work out to? How do I know that's the area of a parallelogram? Remember area of a parallelogram? Take the cross product of the vectors. The magnitude's the area, right? Remember? Still true. So what does this work out to? We got what? The magnitude of 0, 0, and the z component's the only interesting one. So it's xu, yv, minus yu, xv. In other words, the square root of xu yv minus yv xv, yu xv rather, squared, right? I lost my So what I have shown you is that a transformation like this, it really does map, well, it's almost, we're pretty close to having proved it, but I guess we've not quite done it. We've shown that a rectangle maps to a parallelogram, right? And the area apparently scales by this factor right here, right? So what? So what have we shown? We've shown that the area of this thing right here we could write as the absolute value of the determinate of t prime of u naught v naught times change in u, change in v. That's actually, I mean, this, remember, t prime is simply the matrix, xu, yu, xv, yv. If you calculate the determinant of that matrix, that's exactly this expression, xu times xv minus xv times yu. So what's my next step? So I can take a sum over, say, I and j of f of u sub I, v sub j, delta u, delta v, and I can rewrite that as what? Oh, I think I got turned around. No, I didn't. Man. Area of S is equal to we've done all the hard work. I just need to give you the punchline at this point. Let me write down what is true. There's just some gap in my brain at the moment. It follows then that the double integral of f of u comma v, let's say du dv over s, is equal to the double integral over r of f of x of uv comma y of uv, the what's called the Jacobian determinate. So this factor right here gets a special notation. It's sometimes denoted guys, I have annoyingly cannot find my copy of your book at the moment. Can you guys tell me what this looks like in your book? If you look at the change of coordinates section, somebody have it? What's their notation for what's called the Jacobian? Ah, there's one. Thank you. It's killing me. I do not know where my book went. It is driving me nuts.
Maybe the book monster ate it.
The book monster ate it? Well, that would be quite a meal, wouldn't it? Let's see. For some reason, these clowns always put the Jacobian section at the very end of the chapter. They've already been using it for 3 sections before that, but for some reason they think you guys like to have the cart before the horse or something. It's probably true. I'm probably the one that's wrong. Anyway, well, they use absolute value of JUV. Okay, so apparently this is denoted absolute value of JUV in the, well, This makes sense. This is the determinant of the Jacobian with respect to u and v. That's good notation, actually. I like it. Anyway, so whatever you want to denote this as, it's the determinant of xu, yu, xv, yv, absolute value of that thing, du dv. The reason for the presence of this scale factor is because you see that a little change in u, change in v box, right? It transforms over to this little parallelogram with this rescaled area of the Jacobian times change in u, change in v. And that's why this term is present, is because, if you zoomed down at the microscopic level, you can always approximate your curvilinear coordinate transformation with a linearization, and that linearization basically just multiplies the infinitesimal vector by the Jacobian matrix, which gives you a scale factor for the area of the determinant of the Jacobian matrix. So U-substitution is a little bit more complicated here, but when we actually do it, it's not that hard. Let me show you how this actually fleshes out. So I did polar coordinates last time, right? So how do polar coordinates go? We have what? We have x is equal to r cosine theta, y is equal to r sine theta. So the Jacobian with respect to r and theta, well, the Jacobian matrix is what? How's it go? It goes, let's write it out, xr, yr, x theta, y theta, right? What is that? Yeah, cosine theta, sine theta, minus r sine theta, r cosine theta. So what's the determinant of the Jacobian matrix of r and theta? Or you could just say the Jacobian determinant. What's the Jacobian determinant? We've got an r cosine squared theta plus r sine squared theta, otherwise known as r, right? So this theorem, the change of variables theorem, becomes the following for polar coordinates. If we want to talk about some polar domain S and have a function of r and theta times dr d theta, that will be equal to, how's it go? Integral over the corresponding region f of r cosine theta, r sine theta. What's this? R I'm sorry, guys. This is not supposed to be u and v here. This is supposed to be x and y. Otherwise, this is a really, really weird. Well, it's still weird. All right. So this is still not how I want to write it. My brain is broken today. I mean, the theorem I want to write is the following. If we have f of x comma y dx dy over some region, say b, that's equal to the double integral over, say, b prime of f of x of uv y of uv the Jacobian of u and v du dv. So I think it's that I'm changing the roles of x and y in u and v. Like, I think this is the same theorem, but I've changed the notation.
So like that one.
I think these are both right, but
One, you're going from x, y to uv.
Right.
And then you're going backwards.
I mean, pragmatically speaking, this is what we do. This is how we use it. So, yeah, I mean, what I've worked out for the parallelogram, I think, is correct. The question is whether or not, I mean, the parallelogram, words, the parallelogram calculation is correct. What's missing is like an extra stupid sentence or two to explain why I'm going from here to here. Okay, so sorry, Mike. Yes?
Why is it f of x of u of v like in both the top and the bottom? Because you switch them in the first one, but then the second one. Is that part of the missing step?
I don't know. I'm missing the words right now, Daniel. Give me a minute here. So the integral, this much is true. The integral, oh, curses, where was I? Integral over b of f of xy dx dy is equal to the integral, double integral over b prime, let's say, or maybe better yet, let's say b polar. So here's b Cartesian, f of r cosine theta, r sine theta, r dr d theta.
Yeah, that makes sense. Because you had r and theta on both sides of the equal sign first time you tried to write that out.
Yeah, let me think about this for a second here. So, I mean, clearly the role of u and v and x and y are flipped over, right? But this is like the, well,
The top would be f of u of xy d of.
I'm sorry, which top one?
Like that one. Should that be u xy d xy?
I mean, I guess we might write it like this. That would make kind of more sense going back to the picture, right? So we're saying that the u comma v maps to x comma y. So the transported point is called xy. Yeah, so I think we could put xy here. That would be more reasonable. Sorry, is this the same confusion that I inevitably get into when I try to prove the chain rule? Excuse me, U-substitution in Calculus 1? There is something malevolent about the proof of the U-sub. Have you ever seen a proof of U-substitution? You just did it, didn't you? Your instructor had the good sense not to prove it because there is something backwards about the thinking that's needed to prove it. And so I just copied I picked up a calculus book and I started drawing this picture. My hope was that if I followed the picture and followed my heart, eventually we would come to something logical. And I think we did. The trouble is at the end of it, we have to bait and switch you in terms of turning the meaning of u and v over to x and y and vice versa, which is what's bugging you, understandably. Oh, well, I tried. I'm going to stop trying to prove this stupid thing and just use it. I'm sorry, guys. I tried. I don't think what we did is wrong. I just think it's notationally upside down. I wish I could tell you this is the first time this has happened, but inevitably this derivation comes up at the point in the semester I don't have enough time to sit down and really think it out before it happens, and then it happens. So if I'm smarter, I'll just gloss over this and you guys wouldn't even notice.
I think I did see it in Calc 1.
Mm-hmm.
Problem is, when the professor taught, he sort of tended to stand in front of what he was writing the whole time. So, sort of complicated.
I mean, I could go try to do the Calc 1 thing now, and we could see that I get that exactly the same backwards way, but I'm going to sacrifice my pride and go on. There we go. So let's calculate some Jacobians. What's the Jacobian? Suppose you had x is equal to AU, y is equal to BV. All right. So what's the Jacobian determinant for this? Let's see, U derivative is what? A? 0, 0, B. So it's just AB. All right, application. Calculate area of x squared over a squared plus y squared over b squared less than or equal to 1. In other words, calculate the area of an ellipse. So, to do that, we calculate the double integral of the ellipse, dA. Right? Of course, dA to start with we think of as being dx and dy, right? But what happens if you let x equals to AU and y equals to BV? What does that say about U? And what does that tell you? U is equal to what? X over A. V is equal to what? Y over B. So here's the ellipse originally presented in Cartesians. Becomes the double integral of what? Apparently a, b, du, dv. I'm assuming that a and b are positive, all right? And what's the transformed region? We have to change the measure and change the bound. What I'm telling you is to change the measure, we have to calculate the Jacobian determinant. To change the bounds, well, you have to think about how the shape is transformed. I kind of am showing you what happens. See this? See that? Look at the original thing. What's this translate to? Here's your dream of an example, Luke, that requires no pictures, just straight algebra. This becomes what? Also known as the unit circle, unit disk, right? In UV space, though, right? And so that, right, is AB times the double integral du dv over the unit disk. But what's that? Well, assuming that we know that the area of a circle is pi, if it has radius 1, we know that this thing does what? Pi. And so the answer, pi AB. You're like, but how do we know that the area of a circle is pi r squared, right? Glad you asked. See, we can do that now pretty easy. How do we do that? Area of circle. So we'd have the integral over a circle, right? Or disk, rather. X squared plus y squared less than or equal to r squared. So that becomes the integral from 0 to 2 pi, integral from 0 to r. What is dA in polars? dA in polars is r dr d theta. I'm using the theorem I almost proved today. Let's see. Oh, more than I'd like. 1/2 r squared evaluated from 0 to r, and then theta evaluated from 0 to 2 pi, right? So anyway, we get pi r squared, which I just used in the previous example, but here's why that's true, yeah? So how do we change a double integral? The dA, you have to use the Jacobian factor, right? And we also have to change the actual bounds to the new variables, right? Shall I work another example? Maybe? Yeah. Find area of this. This example I'm about to show you is wrong. What I'm doing is wrong, but it is instructive. It's a lesson in what not to do. Now, I'm going to do correct mathematics, but it's going to be painful. So, of course, the area is just the integral over this triangle, right, of dx dy, right? But I can reformulate this in terms of polar coordinates. How? 0 less than or equal to theta less than or equal to pi over 2, right? And how is r bounded here? Well, r is kind of easy on one side. R is less than or equal to 0, right? But what's the upper bound for r? Oh, 0 is greater than 0. True, but useless. Okay, r. Now, what you just did is you converted this to its polar form, right? Which is r sine theta is equal to 1 minus r cosine theta, right? And from that, I can see that r is equal to what? There's a moral to this example, and let's see here. So, and then the dA and dx dy changes to what in polar coordinates? It changes to r dr d theta, and r dr d theta because I put the r bound first, right? We're still bound by that same logic there. And then what? And then you integrate. Let's see here. So that's like 1/2, 1 over sine theta plus cosine theta, quantity squared, d theta. And then how do you integrate that? maybe you thinking we could square that out? So sine squared theta plus cosine, sine squared theta plus 2 sine theta cosine theta, right? Plus cosine squared theta is what we would have had in the denominator, which is 1 plus 2 sine theta cosine theta. OA. Great. Now what? I guess then this is the integral from 0 to pi over 2 of 1 over 1/2 of d theta over 1 plus sine 2 theta.
And then the other thing turns into 1 plus 2 sine theta cosine theta.
What?
Sine squared plus cosine squared on opposite ends.
Mm. So I'm going to actually go back to this. And let's see, let's try multiplying by sine theta minus cosine theta over sine theta minus cosine theta, see if anything nice happens. Eh. See, I need to teach Calc 2 again. I'm getting rusty. This somehow devolves into a secant integral, or a cosecant. Yeah, I mean, this does equal to, I mean, I'm going to put us out of our misery for now. The point is, this integral can be done if you're really strong on your Calc 2 and or not tired. And that does work out to a half. But the point is, this is a formidable ... that I'm not doing in here, right? I mean, if you look at my notes, I actually have the details to this example. All of the gory calculus is there. But what's wrong about this example? Right, I'm using polar coordinates for a problem that's quite clearly a Cartesian problem, right? Now usually you guys have to do the opposite thing. I give you a problem and you have to go, wait a minute, that problem makes more sense in polar coordinates, and then you use polar coordinates. It makes it easier, right? So you got to think, what's the right tool for the job? This is the wrong tool, right? But at the same time, I like this example because it makes you think about how you find polar bounds for other things. Now, this would still be, here's something. If you were faced with the integral, say, of, you know, I don't know, y over the square root of x squared plus y squared dA over that triangle, then all of a sudden this problem is, then this is not just an academic thing that I've done. It makes sense to do it the way we did it because this integrand has a certain polar aspect to it, right? Like this integrand becomes really, really simple in polar coordinates. What is this? Yeah, this is sine theta, and then dA becomes, of course, r dr d theta. And then so when you actually went and did that integral, you'd have a sine theta upstairs, and all of a sudden this becomes a U-substitution. It's easy to do. Whereas if you tried to do it in Cartesians, it would be beastly. Yeah?
That integral would be r sine theta over r times r dr theta.
I'm sorry?
In the numerator of
Mhm.
the integrand, you have r sine theta, and the denominator you have
Oh, no, no, that's r. So y is r sine theta, that's r sine theta divided by r. That's just sine theta. The r here is coming from the change of coordinates. All right, so my point is there's two things at play for why you'd want to make a change of variables. The one is, and most often you want to make a change of variables to make the bounds become easy. That's usually what we want to do. But the other thing to think about is the integrand unmanageable in my current coordinate system? Can I change coordinate systems to make it manageable? This is such an example of that. Because you don't want to integrate 1 over the square root of x squared plus y squared with respect to x or y. It's miserable, right? I mean, you can do it, trig substitution, right? But that was partly a joke. What if you have 3 variables? What's this look like in 3 variables? Like so, right? And you know what happens? You just add another letter. Let's see, UV, I guess we'll do W. W. It's one of my favorite examples. It's nice and simple, but it illustrates the method. So this would be the Jacobian of this transformation on R3. It's just a rescaling of each coordinate, right? What would the application here be? What if I wanted to calculate the volume of an ellipsoid? What is this? So this, in terms of the above transformation, becomes what? So under this substitution, the ellipsoid becomes the unit sphere. So I can calculate the volume of the ellipsoid in terms of dx, dy, dz. I don't know. I mean, you're welcome to do that if you want to. It involves a genuinely triple integral and square roots. It's quite unpleasant. Or you can do a substitution, and substitution takes you to the unit sphere. And the Jacobian determinate is what here? It's ABC, du, dv, dw. ABC is a constant. It pulls out, and you're left with what then? So this works out to 4/3 pi. So you get 4/3 pi ABC. Now I have put the cart before the horse here. How do I know that the volume of a unit sphere is 4/3 pi? You're like, well, some math teacher told me that back in college algebra, and I remember it. I don't think that's a very good reason for the volume of the unit sphere being 4/3 pi. I mean, it's true, but it may not be part of your existence, part of your experience or not, I don't know. But what do we need in order to do integrals with respect to spherical coordinates? What do we have to calculate? Right, so for spherical coordinates, spherical coordinate change, what's the theorem look like for that? We have x is equal to rho cosine theta, sine phi. Y is equal to rho sine theta, sine phi. Z is rho cosine phi, right? So this gives us the Jacobian with respect to rho phi theta. Jacobian matrix of what was the Jacobian matrix going to be? It's going to be cosine theta sine phi, sine theta, sine phi, cosine phi. Now I differentiate with respect to phi. What do I get? Do you guys agree? So that's the derivative with respect to phi of x, y, and z respective. And then last but not least, the derivative with respect to theta gives me minus rho sine theta, sine phi, rho cosine theta, sine phi, and finally, my favorite, 0. Yeah. Now what we need to calculate, though, somewhat unpleasant, we need to calculate the determinant of the Jacobian of rho phi theta. That's what we're going to need to know in order to make spherical coordinate change, right? This one gets us warmed up, right? But it doesn't really prepare you for this. There's about a 50% chance I'm going to get this wrong. Just warning you. So cosine theta, sine phi, and then looks like a rho squared sine squared phi cosine theta minus rho cosine theta cosine phi minus rho cosine theta cosine phi sine phi. And then finally minus rho sine theta sine phi times minus rho sine theta sine squared phi minus rho sine theta cosine phi squared. I mean, on first glance, you'd be like, well, what hope do we ever have of doing spherical substitutions, right? I mean, this is awful. But some stuff collapses down here. Let's see if we can't find some participants here that are all the same. Rho squared on every term. I like that. We'll factor that out. Is there anything else on every term that we could factor out, maybe? Yeah, there's a sine phi here that I'll factor out. There's a sine phi here I will factor out. And I will also factor out this sine phi. So quite clearly we have a sine phi we can factor out. So you have picked up on there being a sine squared and cosine squared combination. So this thing drops down to just minus rho sine theta. I like it. So let me just collect our thoughts here. We've got ourselves a rho squared sine squared phi cosine squared theta. I brought the cosine theta over to here. And then plus what? Plus rho squared. Looks like a cosine squared theta. Cosine squared phi. Oh, sorry. Yeah, I already fixed it. All right. And then we're to this term, which apparently is just plus rho sine squared theta sine phi. Oh, no rho. Sorry.
That
Scooby-Doo. Oh, sorry. It's awful. All right, look at this. Oh, man.
Yeah, actually the last term there's no sine phi either.
Oh,
It's sine squared theta. It's less. It's rho squared minus.
thank you. What's this? What's this? Not 1, but cosine squared theta. And then that. And so there we go. Hey, it looks like there's still hope for spherical substitution. So basically, here's the way it works. dv in sphericals is rho squared sine phi d rho, d phi, d theta. And this is how I remember the substitution. So this is the spherical volume element. We do this calculation once. And then maybe again on your test, but just once in class, all right? I'm not going to go through this again. I don't really want to grade this either, but I mean, it is what it is. How about cylindrical coordinate change? You have x is equal to r cosine theta, right? Y is equal to r sine theta. Z is equal to z. So basically, you just get dx, dy, dz is equal to r dr, d theta, dz. So here's your dv in Cartesian and also polar coordinates. I mean, if you want, you can take what we did over here to get cylindrical. What do? If you study this for cylindrical, all that happens is you get 0, 0, 1. There you go. This is the Jacobian for r theta z.
Adding the extra zeros and the 1
Yeah, the way the determinant works is if you have it in blocks like that, you can multiply the determinant upper block times the determinant of the lower block, so it's literally just r times 1. Oh, sorry. I'm using forbidden techniques. All right, now let us go back to the problem of calculating the volume of a sphere and dispatch it like the silly little punk that it is. All right, so here it is. Example x squared plus y squared plus z squared less than or equal to r squared. How do you rewrite this in terms of spherical coordinates? 0 less than or equal to theta less than or equal to 2 pi. 0 less than or equal to phi less than or equal to pi. 0 less than or equal to rho less than or equal to r. What was complicated has become rectangular, right? What was the bounds, if we looked at that last class, it would have been, it's awful. Now, simple, right? And then, so the integral over the sphere, dv in x, y, z, we can rewrite as integral from 0 to 2 pi, integral from 0 to pi, integral from 0 to r. Apparently I did. And then dv in sphericals, as we just worked out, is rho squared sine phi d rho d phi d theta. What'd you get? You get theta evaluated from 0 to 2 pi. You get sine, what's the derivative? What's the integral of sine phi? Minus cosine phi, right? Evaluated from 0 to pi. And you got yourself a rho cubed over 3 evaluated from 0 to r. This is one of those times that I want to multiply the integrals because I can get away with it because the bounds are rectangular.